SP2010 was like way long. It had the capacitors in it. It had everything in it, but it had circuits, had all this stuff in it. And this book breaks it down into more manageable bytes, I guess. All right, so without further ado, though, let's go ahead. Gosh dang it, I forgot to bring paper. Oh, well, that's all right. Let's go ahead and take a look at this guy. Okay, I haven't done any of this. Oh, I got 107 points for that one. All right, but that's good. Energy and capacitor. Let's take a look at this problem because this one can be kind of ugly. All right, now some things you've got to keep in mind. All right, so let's work through this one. We're going to work through about 3 of these capacitor type problems so that you can do them. All right, now things you got to keep in mind. Did I at least bring those notes? Probably not. Yeah, good. All right, things you need to keep in mind when working with capacitors. First of all, we are going to do nothing but work. Aha, see, stole it. Okay, now it's back. Let's turn on the lamps. Let's see what happens. See if we can get more light on there. Come on now. There we go. Too fatty. Good. All right, now, here we go. We're going to have this. We're going to have the capacitance of something is equal to that permittivity of free space, that little E naught, which is like 8.85 times 10 to the negative 12, something, Coulomb squared per newtons per newton meter squared type thing, okay? That's your permittivity of free space, all right? Times the area of the parallel plate capacitors divided by the distance that they're apart, okay? Divided by the distance that they're apart. The other thing, so we're going to always keep this in mind. The other thing that we have to keep in mind is that voltage equals ED. Is that correct? Yeah. Yeah. Okay. Voltage equals ED, and so we also know this, that Q equals the capacitance times V, all right? And so you can actually say that so if I put this, let me rearrange this for you. Let me get all these little equations down instead of just trying to derive them right while I'm standing up here. That's no good. All right, here we go. What chapter is this anyway? 16? They're killing me. All right, here we go. All right, now we found it. Okay, so now that's what our capacitance equals. Now I'm going to be careful here because I screwed it up big time. It was pointed out to me last time, which was good. Hey, don't you know how to divide? Not today. But anyway, we're getting better. So capacitance is equal to Q over V. All right, now then, and the energy. Now the energy we consider to be inside that electric field. All right, the energy is inside the electric field, and so the energy contained in a capacitor is equal to 1/2 QV, which we could rearrange as Q squared over 2C, or that also equals 1/2 CV squared. All right, so this is the thing I was after here. So if we've got V squared, that also equals, this equals 1/2 C, which is echo dot A over D times ED squared, which would be E squared D squared, which would also be E squared times D squared. All right, now right away you're going to say, well, wait a minute, you can cancel that D. Yes, you can. Yes, you can. You can cancel one of those D's there, everything else. But I'm just going to leave it like that for right now. So this is what we need to be able to answer those two long we need these equations and understand how they work to be able to answer those long problems. All right, so here we go. Here we go. Let's work through it. I think I think it'll be worth your while. I hope I don't bore you too much here with this as we go through one of your longer. I think this homework problems, yeah, it goes on forever. All right, anyway. Okay, so it says find the energy of the capacitor of terms C and Q by using the definition of capacitance and the formula for the energy in the capacitor. All right, express your answer in terms of C and Q. Okay, so which one do we need that's only in C and Q here for this energy right here? Here's what you do. First of all, this is also an exercise in how to do these things. Okay, first of all, it's going to be 1/2. I'm going to put the 2 in when I get done. Now, what did we have over here? Hold on a second. Let me flash back real quick. I know this might be. Which one, if we want to measure the energy in just terms of Q and C, which one of these guys am I going to use? Q squared over C, over 2C. Right, exactly. All right, so that's what we'll do. We'll switch back. So we got 1, capital Q. And then you go up here and you do the squared thing. Most of you guys are over 2 times C. Most of you guys are, please be right. Help a brother out. Yes, it was right. Okay, now, so this is good. Most of you are mastering physics rangers by now, so you understand how to input all those things. All right, so now let's find the energy U of the capacitor in terms of C and V by using the definition. Oh, okay. So which one should we use on this one? 1/2 CV squared. Thank you. Good, yeah, just bark them out there. 1/2 C V squared over 2 submit. All right, good. There we go. Or CV squared over 2 or whatever. All right, now it gets tricky, I think. Aha! This one. This is why I did these ahead of time, so I wouldn't get stuck just flailing around, but I probably still will flail around here a little bit. It says a parallel plate capacitor is connected to a battery. The energy of the capacitor is U0. Okay, fine. The capacitor remains connected to the battery while the plates are slowly pulled apart until the plate separation doubles. The new energy of the capacitor is U. Okay, we're going to leave it plugged in. So this means coulombs are still building up, but what stays the same if it's still hooked to the battery? The voltage. Very good. Yes. All right. You guys got it. However, we've got a situation here. Where we're going to be spreading this thing apart. So I think what they want us to do, the old energy was this. So Q is going to be growing, so we want to use this. We want to use U. Oh, you probably want to see what I'm doing here. Method to my madness. All right, so let's say this. U0. Okay, so the original U is going to equal, we're going to use this. It's 1/2 C naught V squared. Okay, now V is not going to change, but C will. All right, now what we have to do here is we got to go, okay, so U0 is 1/2, and I'm going to go ahead and use this echo naught times A over D times, now it's going to be E squared, D squared. Okay? E squared, D squared. All right. Now, I don't need to worry. Yes, I do. Yes, I do. I need to worry about that because when I change the voltage, because the voltage is going to stay the same. Okay? The voltage is going to stay the same. Or do I need to worry about that? No, let's not worry about that because we're going to let the voltage stay the same. Yes, thank you. That was the whole key to that problem. That was the whole key to that problem. It's when we unplug it, it's when we take it away from the capacitor on the next one that we've got issues. Thank you for helping me out there. All right, so now what was I supposed to do? What did the problem say? We're going to double this distance, right? So here's my original one, is just this. It's echo naught A over V squared over 2D. Now, I'm going to double my distance. So now, what do I have down here? I got 4D now, right? So what's that? I think so. Pretty soon. Yeah, I better do it slowly, though, because I'll screw it up if I don't do it. All right, so the new U is equal to equinat A V squared over 4D. Okay? And what did they want? Did they want U naught over U? Is that what they wanted? Let's go back and look. Yeah, they wanted U over U naught. So this puts me, so I've got this. I've got equinat at A V squared over 4D. Oh! I got to switch the screen. Sorry. I got all this tech. There we go. Here I am. I'm right here. This is how far I got while I had you in the dark. Divided by. So basically, I'm going to wind up, what was trying to be said was I've got 1/4 over 1/2, which is 1 over 2. Boy, I hope that's right. If it's not right, the class is canceled. I've said that before and I've been wrong and I didn't. I have no credibility. There we go. Yes! 0.5. They wanted 0.5. Fine. Whatever. Okay, now we come to a little bit trickier. It's going to be a little bit trickier. We've got a parallel plate capacitor is connected to a battery, right? The energy of the capacitor is U naught. The capacitor is then disconnected. So what happens when I disconnect that thing? What's going to happen? The charge will stay the same, but what's going to change now? The voltage. The voltage is going to change. Okay? And voltage is equal to ED. All right? And now E is going to stay the same, but the D is going to change. Now, what did we do here? We're going to are slowly pulled apart until the plate separation doubles. All right, believe it or not, guess what happens if the electric field stays the same and I separate the plates further? What happens to the voltage? It actually goes up. Yeah, so in this case, the voltage will double. All right, and so and the key is going to stay the same. So let's use this guy. All right. So we've got this. Here's what I did, and I know it's probably painful, but here's what I did. I said that U naught, the original U, is going to equal 1/2 the permittivity of free space times A over D times E squared D squared. Okay? There's my voltage squared. Now, I said, oh, if I double the voltage, or if I double that space between the two, now then U is going to equal 1/2 E naught A over 2D times E squared. Now, what happens when I double my voltage right here? What happens when this is doubled? What's it turn into? 2D squared or 4D squared? If I take 2D and square it, what do I get? 4D squared. So this will be 4D squared. Oh, look at this. I love it when things cancel. Those all cancel. So my new U, we're going to cancel that too. Just make that D. Now follow along to my madness here. So I've basically got E naught A E squared D. Right? Yep. Divided by, cancel that, 1/2 E naught A over E squared times D. All right, so all these guys cancel. Bang, 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 bang. So I've got 1 over 1/2. What's that ratio? What? 2 to 3? What's that? Oh, yeah, it'd be 2. All right, good. Geniuses. Good idea. Switch it back. All right, so this is equal to 2. Oh, man, how long is this? Gosh. All right. This is killer. Parallel plate capacitor. All right, I'm going to spend about 1 more minute on this thing, and then I've had enough. All right, parallel plate capacitor has an area and a plate separation of D, and it is charged in voltage V. Use the formulas from the problem introduction to obtain the formula for the energy U of the capacitor. Oh, we've already done that. You can do that. You can do that. EA over D times V squared. I'm not going to go through all that. 1/2. Don't forget to make it 1/2. And then all the rest of them is the same thing. Okay? So like on this one, it says a parallel plate capacitor has area A and a separation of D and is charged so that the electric field inside is E. Use the formula. Okay, and then yeah, you can do it. I've already shown you how to do it with E anyway. And the energy density of the electric field is the energy density. They explain what the energy density is. Basically, you just divide by AD, which is your volume. Okay, so you just take the energy density. So you just take out the A and the D, and so your energy density becomes 1/2 echo naught E squared. That's your energy density. Because A times D, what's area times depth? What does that equal? A volume, right? So anytime I take, so when they talk about the energy density, they're talking about the joules per meters cubed, okay? And so when I had that total energy on there, if you notice I've got A times D, well, that's a meters cubed. So if I divide by that A times D, if I divide by the volume that it's taking up, if I divide by A times D, I just wind up with 1/2 echo naught E squared. And that's your energy density. All right, so that's enough on that one. Whew, no more, no más. All right, now, okay, and then this one is much easier. It's more of the same thing. All right, for capacitors. Oh, this one's kind of cool. I have no idea. Okay. All right. In the figures, oh, what's the charge Q on the capacitor? The capacitor is connected to an applied potential VAB. All right. So here's the story. In other words, we've got a voltage going through here. All right. It's got a voltage. It's going to be the same voltage. It's going to go through this as not so much that. This one might be kind of tricky. I should have probably looked at this. All right. We'll come back to that one. Actually, I don't think it's all that tricky. It says, what's the charge Q1 on C1? All right. If you know what C1 is and the capacitor is connected to an applied voltage VAB, after the charges have reached their final values, the charge Q2 on the second capacitor is, so you just have to work it backwards. I see how it works now. All right, so if I've got 40 microcoulombs of charge here on C2, all right, and I'll have to find the voltage of what voltage AB is. You know this. In other words, C2, whoops, you don't know that. Hold on a second. I'll get this down here in a minute. All right, in other words, you know that C2 was some farads. I can't remember. Some kind of microfarads, all right? And you also know this. You know that Q is equal to CVAB. Okay, Q is equal to CVAB. So if they give you Q and they give you C, can you find that voltage? Yeah, and then you can go back through and you can find what Q1 is, you can find what Q2 is, all right, on those capacitors, and then you can find what Q3 is. also. Okay? That's wrong. Here's the deal. On that problem, what we have to do is we have to find the total capacitance. Okay? We have to find the total capacitance of that thing. Here's how you do it. Let me just do it this way. Let me just give you an example of how to do this problem. All right, so here's what we've got. We've got this thing shooting up here because you guys aren't used to seeing this kind of stuff before. All right, and then it comes around like this. And then I got a capacitor here, right? And this was C1, C2, and C3, correct? All right, and the voltage that's going through A and B, I've got a voltage that's being pushed through here and here. Now, what happens is I've got a total capacitance here. Now then, are these capacitors, I thought I grew that when I was 14, but anyway, are these capacitors in series or parallel? Both, exactly. Which ones are in parallel? C1 and 2. Okay, so for capacitors in parallel, how do you find what their capacitance is equal to? You just add them together, right? So CP is equal to C1 plus C2. All right? So, and now, so we've got C1 plus C2 plus C3. This is how you find the total capacitance of the thing, all right? And so you do this. So now I just shrink this down. It looks like this now. Now it looks like this. So I've got CP and C3. What are those? Are those in series or parallel? Series. They're in series. Okay? And so 1 over CS equals 1 over CP plus 1 over C3. Okay? And then what you have to do is, now remember, you can't just flip these guys and do it, otherwise they'd be in parallel. That'd be too easy. We don't want to do that. All right, so basically, when you just have 2 like this, it's actually not too bad because you multiply on top and you add on the bottom, and that's basically what your answer comes out to be. But let's go ahead and do this anyway. 1 over CS then would equal, if I multiply this by C3 over C3, multiply this one by CP over CP, so 1 over CS is equal to C3 plus CP over C3 times CP. All right, and so in series, those guys are going to equal C3 times CP over C3 plus CP. All right, because you got to flip it now. Now you can easily flip it over. All right, and in fact, electricians, when they're dealing with 2 resistors, or they're dealing with 2 capacitors, when they're dealing with 2 resistors in parallel, or when they're dealing with 2 capacitors in series, they know that the total of them is you just multiply them and divide by the sum. That doesn't work if you get more than 2, though. It doesn't work if you get more than 2. All right, so now this is the total capacitance of this thing. Here's the total capacitance. So now I could find, so Q, the total charge Q, is equal to this whole CS times VAB. All right? And then you can figure it out from there. All right. Okay. All right, good. Good. All right. Let's go on to the new stuff. And if you get stuck on that one, we might look at it again on Friday. All right. In fact, I'll bring the solution to that. Yes?
I was a little confused on that problem because they don't give us a number from VAB.
Right. You've got to use it. In other words, what we did was you have to use. You're going to find that Q over CS is equal to your VAB. That's why we went through the total charge in that thing. All right. It's one of those kinds of problems. All right. So now, let's take a look. Okay. Here we go. What I've got up here, this is a battery. Okay? This is a battery. And all its negative charge, it's got all this negative charge down here. Potential difference is down to the right. Okay, now, I've got it pretty much cranked up here. That's the desired voltage. Now, if I want to change the voltage, if I make it 0, there we go. Here comes my little chemicals. It's magic, right? How that happens. I get this nice and even. Now watch when I watch the arrow there. So I come get them, and it slowly takes them. There it goes. Get the voltage to where it's almost even. All right, there we go. One more guy comes over there. Let's get some more voltage. Basically, I'm turning the battery around the other way. There we go. Boom. There they go. All right, that's the chemical reaction that's going on in batteries. Now, what happens is, basically, what I'm doing to you here is I'm starting the chapter 17. Did I do a battery circuit? Well, here's kind of a battery circuit. All right, now, here's what we're going to do. Here's a battery, all right, hooked up to a thing. Now, this thing's not working. Let me show you what happens with a capacitor, because this is what I'm going to discharge this capacitor. Boom, there. Now, look what happens. The battery starts to fill it back, pumps a bunch of negative charge into here. It attracts the protons over here, and eventually gets to the point where nothing else can flow, and so it eventually stops. All right? So it eventually stops. Then you discharge the capacitor, boom. And you can fill it back up again. Boom, boom, boom. All right? Now, and the voltage difference, real quick, get my little voltmeter here, put him down here. Voltage difference on the battery is 9 volts. And so when I put this up here, since it's upside down, the voltage difference on that guy is negative 9 volts. Or if I just leave it the same. He's 9 volts too, once he gets all charged up. So basically what I could do is remove the battery. I could hook these guys together. What's going to happen when I hook this wire with this? What do you think will happen? Yeah, it'll flow for a while until here's what you do with your phone. Here's how your phone works, your phone charger. All right? Then, I've got no more bars. Okay? I better charge it back up again. So when you hook, oh God, this frustrates me when this happens. When I can't get the, man, that just pisses me off. There we go. Now, there. Now it fills it back up like that. All right. There. Now your phone's charged. Okay. And once the phone gets charged, then it's got another switch in there. I'm sure that what happens is it's just like removing the battery. And so it goes, all right, make a call. Oop, okay, done with the call. Make a call. Oop, done with the call. And see eventually. So that's what's going on inside your battery. All right, because remember what I've always said. Nothing else. When you take all these science classes that you pre-meders, pre-dental, all that stuff are doing, if nothing else, it'll make you a good parent. All right, so when your kid asks you questions, you'll be able to answer them. All right, and if you give the answer detailed enough and confusing enough, the way I teach you, they'll never ask you another question again. So you get out of it. All right. Okay, so now, so that's battery and voltage. Now, let's talk about chapter 17. Let me go to those slides. This is so much fun. Oh, yeah. Did I have a quiz? Yeah, we're going to do a quiz, and the way we're going to do it is I'm going to give you some problems based on what we're going to learn here. All right. Basically, chapter 17 is Ohm's law, OHM. All right, Ohm's law. That's basically what it is. Now we're going to get into a thing called current. All right, we're going to get into a thing called voltage or EMF, electromotive force. All right, and we're going to get into a thing called resistance. And V equals IR. All right. So here's how I want you to do the quiz. I want you to be able to take your notes and do the problem on one side so you don't turn in your notes. All right. And we'll just ask questions. We're not ready to do it yet. I just wanted you to kind of get ready. So here we go. So let's go to Start Programs. Let's go to Microsoft Office. Let's open up a document here. Y'all can see a method to my madness here as we come down to Q. And please have chapter 17. There it is. Open. Sesame Street. There we go. Now, boom. Slideshow. View show. All right. Here we go. Now, this is, I want you to look at this chart. This is a thing on circuits, so you get used to seeing what a circuit looks like. All right. Now, normally they'll just put the battery in there and say it's V. The reason they have this electromotive force, this is the E for electromotive force. And we know it's not a force, but it does push electrons. All right? Because we know this. If I have a battery and I take a wire and I attach it to the negative end and to the positive end, what's going to happen to my fingers? They're going to get really hot. So what's going to happen because that battery is pushing electrons. So that's why they call it an electromotive force. It's not an F equals MA type force. It's voltage. All right? And what they've got here is they're saying, hey, there's a little bit of back EMF is what we call it inside a battery because there's internal resistance inside the battery. So even if you have a 9-volt battery, it's really probably 8.95 volts because there's some internal resistance there. That's just what they're showing here. And that'll equal your amperage times your resistance. All right? There's chapter 17. Are you ready? You're done. You've got it all. You've learned it all. That's all there is to chapter 17. V equals IR. And so here we go. Now you should be ready to, so we're going to look at batteries and direct current, DC. Okay? And we're going to look at current and drift velocity. All right? One glaring hole that Tingy and Saad would be able to say I have in my education is, I don't know what the Hall effect is, but it's something. And maybe they'll explain it. I'm going to go ask Dr. Livesley. I don't want to ask Tony Caruso because he'll think you're an idiot. But anyway, so I'll ask one of them. Say, what is the Hall effect again? I've figured it before, but I can't remember what it is. And we're going to do resistance and Ohm's law and electric power. All right? 4 little things in this chapter 17 that's going to be added to your toolkit of knowledge. All right, so we've already seen that. I kind of liked my little magic show, the Kansas Science Standards for showing the battery. But here's the actual anode is negative, cathode's negative, anode is, wait a minute. Anode is negative, right, because it's anti, cathode is positive. Right, all right. So here we go. Okay, so you get that voltage, that EMF, electromotive force, pushing charge. Okay, in a complete circuit, electrons flow from the negative electrode to the positive one. The positive electrode is called the anode. Ha-ha, that's what I thought. Now I've said it 3 different ways. All right, so you can't catch me in a lie here. The negative electrode is the cathode. Okay, the battery provides a constant source of voltage. It maintains a constant potential difference between its terminals. So if I keep up that constant voltage, all right, if I keep up a constant voltage, then it can always push charge until its chemical energy runs out, and then it can't do that anymore, right? Okay, then it goes dead. All right, and you got a dead battery. Okay. The positive and negative, the electromotive force, the potential difference between the battery terminals, okay, is called the when the battery is not connected to anything, it's called the electromotive force, the EMF of the batteries. All right. So it's 9 volts, 12 volts, whatever. Now, the one thing that we do here, I want you to understand something. Eventually, in a couple chapters, we're going to get to AC, alternating current. All right. Now, to get lights to work, the current doesn't have to just go in one direction. All it's got to be doing is moving, okay, to get lights to work. So when we're doing AC, and I'm bringing in my friend Mike Kelly at the first week of March, and he's the power professor here for the electrical engineers, and he's a 30-year veteran of Kansas City Power and Light, and he'll explain to you the whole grid system and how, when you flick on the lights, why that happens, and everything. But when we've got AC, we're bouncing back and forth. We're moving the current back and forth. And that's okay. Just as long as current's moving, you've got power, okay? When the current stops moving, that's when you lose power. All right. So it doesn't matter if it's AC or DC. Okay. It's just that AC is much safer to work with. AC can give you tremendous amounts of voltage with small amperage. All right. Okay, now, batteries and direct current. So here's what our thing looks like. We've got a little internal resistance here. Got a little bit of internal resistance here, but mainly for the most part, we're going to be looking at a voltage V and an R, a resistance. Okay? All right. Here they're hooked up in series. Okay? Here the voltage is hooked up in series. And so that means I've got V1. That's just like stacking batteries. I stack the batteries in a big old flashlight, one of those big flashlights. Put a bunch of D cells in there. Okay. Then I get my total thing, and the light bulb provides the filament, and the light bulb gets hot, provides the resistance. Okay. And when that filament and light bulb gets hot, it glows. That gives us light. Okay. And that's what Einstein. The other guy starts with E. Edison, thank you. All right, that's what Edison was looking for. Everybody knew that this would work, but what he was trying to find was what material won't burn up just like that. All right, I need a material that'll last a while. All right, and it's got good resistance and all that kind of stuff. All right, so there they are hooked. So when we've got voltage hooked up in series, it's just V1 plus V2 plus V3. All right, when we hook it up in parallel, when we hook voltage up in parallel like this, hook it up like this, then the amount of voltage that's going through, that's crossing through here, is just equal to one battery. All right. All right. Okay. All right. Now here's the way things look. Here's your circuit symbols and all that kind of stuff. All right. Here's the first quiz question. Let's answer this. All right. Let's say we got something that looks like this. Oh well, shoot. Let me just put this up here. I'm going to draw it. This will be much better. You can't see that at all, can you? There we go. Now you still can't see it. I think I got to autofocus. Oh, zoom in. Do something. Stand there and look. There you go. All right. Can you see the diagram at least? I know it's probably... All right. Here we go. We've got voltage, voltage. First of all, the long side, is that the positive or the negative? Positive. That's the positive side. Now, by convention, when we start working problems, when we get to the next chapter, we're going to say that the current moves from positive to positive, okay? Like that. All right, so now, these two things are hooked up in what? Yeah, they're hooked up in parallel, actually, okay? So, here's the deal. They say this. They say, all right, this shows a circuit connected in parallel to the bulb. Now your answer, you're going to put your name, 1, and it's going to be A, B, or C. I don't want all your notes and all that stuff, so turn it in a separate sheet of paper. It says, because it is assumed that the wires have no resistance before the switch S1 is opened, the voltage across the light bulb equals V. that is VAB, the voltage across here equals V. The reason for that, it's in parallel. Okay? They're in parallel. Okay, what happens to the voltage across the light bulb when S is opened? Click. I turn S off. Okay? In other words, now, if I open up this wire, is anything flowing through here? No, nothing's flowing through here. So now, how much voltage is going through VAB now? Is it V over 2? Is it 0? Or is it V? Those are your three choices. Discuss among yourselves. Rhode Island. It's not a road, it's not an island. Discuss. What? Yeah, she loves it every time. Right. All right. I want you to put A, B, or C. Which one is it? Is it V? Which is, oh, the answers are this. The voltage remains the same. Okay, A, the voltage remains the same. I'm sorry. B, the voltage drops to V over 2. Or C, the voltage drops to 0. Which is it? Any ideas? Anyone take a stab? A? Really? Yeah. Dang. Geniuses. Yes, it is A. It is A. It is going to be the voltage that you put across there. Very good. Very, very good. And that's why we wire our houses with a lot of things. That's why we wire them in parallel. All right? So that if something goes out, then the rest, if you blow your TV on the thing. By the way, just to get an idea of how much voltage things take, let's get just an idea of what's going on just in general. How much voltage, for those of you that are from foreign lands, you might not know this, but for those of you who grew up here in the United States, how much voltage is coming out of our wall socket? 120, right. It's about 120. There's a little back EMF in there, so it's about 117 or something like that. In Europe and Asia, it's what? 210 to 220, right. So whenever you move over there and you bring all your U.S. appliances, like I had to do in all those years I was in the military, you've got to bring these adapters and converters and stuff like that. Otherwise, you burn up your stuff or your house down. And the Japanese really frown on that, okay? They don't like that. All right. Now, okay, so now, so 120. So 120 volts are coming out of here. How much voltage does it take to run that HD TV that you have, 42-inch screen? What? 15 volts? No, about 15 amps probably, or 10 amps. How many volts? You're only getting 120 out of the house, into the house. How many volts are you getting though? It takes 50,000, between 35 and 50,000 volts to get that HD TV to work. Now, how do we ramp it up? We use a thing called capacitors. We store a bunch of charge, then discharge it. Boom. That's one way. But the most common, so we build circuits with nothing but capacitors and a thing we're going to learn later on called transformers. Once we learn about magnetic fields that you build up that can take that 120 volts and ramp it up to 50,000 for you, okay? That's why with your regular television, which takes about 19,000 volts or so, between 15 to 20,000 volts, good old tiny TV, when you turn it on, it'd come on. But what happens with an HD when you hit that on switch? It takes a while. That's because those transformers and those capacitors are building up charge so they can work, okay? All right? Okay? All right. Well, that was good. Oh, shoot. We're out of time. All right. So, one quiz question. Make sure you turn that in so I can get that to my boy Yang so he can get that in. There we go.